derivatives and integrations are defined in their own way, no connection. The derivative and the integrations are defined in their own way. The next part is focused on their interconnections, how they are connected. This is much more important. And that's why the fundamental theorem of calculus comes up, which fuse the integration and differentiation. Fuse the integration and differentiation. That's good. So let's see how they're connected. Okay, so they're connected like this. First of all, f from a to b to r, it must integrable, is integrable. This is the condition. So the first result helps you to compute the integration and differentiation, like how to compute the integration. So another function that is developed, capital F, okay, which is also defined from a to b. This is a computational aspect. This is defined as if f is a function, if capital F follows this, then you can show that the fundamental theorem of calculus says that a to b fx dx is nothing but capital F of b minus capital F of a. This is the computation part, okay? This is the computation part. Which tells you, instead of doing the calculation, instead of doing all this integration calculation, if you just find a function which follows this and find fb minus fa, that will also suffice. This is what it's telling you. If you just find a function as an f dash of x is equal to capital F small of fx, okay, then integration is defined as capital F of b minus f of a is equal to this. That's number one. Number two, the second part. This is, you can see it helps you to compute things easily, okay? And the next part is that if you define fx like this, say fx, you can define it as integration a to x fx dx. If you define it like this, then you get the following properties. If you define it like this, you get the two properties. Number one, you can prove that fx is continuous on a comma b and fx is differentiable on a comma b and f dash of x is nothing but f of x. Okay, so the second statement actually gives you the idea that the second statement actually gives you the idea that you can, you know, if g is integrable, then there exists a continuous function capital G of x जिसका डेरिवेटिव करके, this is the indefinite integration that we all talk about. This is the indefinite integration. This is the indefinite integration. Oh, sorry, I did a small mistake. This is differentiable. Sorry, I did a small mistake. This is not true. F is not always true. If you define like this, it's always not differentiable. If it's differentiable, then we get it, okay? But if you define it like this, fx is not always differentiable. Not always differentiable. But if small f of x is continuous at C belonging to A comma B. If this is continuous, then it turns out that capital F is differentiable at that point. So what we get? We get that integration of a function may not be always differentiable. Integration of a function may not be always differentiable. Okay, but if the function is continuous, then its integration is differentiable, and f dash of x at that point, f dash of c at that point is equal to that. This is the idea. So it tells you that a discontinuous function can be a derivative, can be a, I mean, you can integrate a discontinuous function to get a continuous function. You can integrate discontinuous functions. That's what it's telling. That's the idea. Yeah. So consider the A to B scenario, fx. Okay. Here it's capital F of x. Capital F of x is defined as A to x fx dx. Okay. Now it's telling that f is integrable. Niska is always continuous. The integrand where it's coming up, this is always continuous, okay? If f is integrable. So in some sense, it's telling that you can integrate discontinuous functions too. And also it's telling that, but if f is continuous, then it's turning out to be differentiable at that point. Okay, if you also add the condition, if f is differentiable, you will see that fx is double differentiable. So if f is n times differentiable, you will see that it's n plus 1 times differentiable. So it's like one dimension extra. Integrable, it goes to continuous. Continuous, it goes to differentiable. Differentiable, it goes to double differentiable. So that's the idea of, this is the idea of the integration, that it makes it one dimensional more in some sense. So you can prove, so this is the basic idea, okay? This is the basic idea. And you have things like integration by paths and all this stuff. So do you need me to teach all these integration by paths and indefinite integration, guys? I don't think it's important. Like all you have done in your 11 and 12, all this integration by paths and all the things. I will give you a PDF where all the formulas are written, okay, of the indefinite integration. So do you need me to teach them? And I don't know. I don't want to waste your time by doing silly stuff. Do you want to do those integration by paths and those things that you have done in 11, 12? Right? At least like what you think, comment down. If you want, yes, tell me. So now you guys are ready with all the arsenals to do integration problems. It's called the mean value theorem. MVT on integration. So we have already seen if f is continuous on A to B. So the idea is that we can differentiate integrable functions, okay? Sorry, we can differentiate discontinuous functions. Okay, we can differentiate discontinuous functions very easily by using that limb soup idea. Okay, but I will tell you how to do it practically. That's the next part. But using the differentiable, like we can prove it. Okay, I mean we can show it that we can do discontinuous functions if the number of terms or number of discontinuous are finite, even countable. But we will not go into that too many, like not too depth wise. But the idea is that if it's continuous, then you have seen that if is the capital F is differentiable, right? So capital F is differentiable. So you can write that f of b minus f of a by b minus a is equal to sum f dash of c, where c is between a to b. Which theorem is this? Which theorem is this? Write down in the comments. Which theorem is this? How we can write this? Mean value theorem, right? Very good. We can write like this. So we can write that fb minus fa is therefore what? B minus a times f dash of c, which is nothing but b minus a times f of c. So we get fb minus fa is what? It's integration a to b f of x dx. So we get that if f is continuous, we can get a c such that integration can be written as this times this, which means intuitively that if you have an integration like this, a function like this, okay, a to b, there exists a point c such that at that height, the area of the rectangle, that is f of c times b minus a, the area of this rectangle is same as the area under the curve. Okay, that is what it tells. The area under the rectangle is same as the area under the curve, the green stuff. That is what it tells. This is one interesting problem in application. We'll end with this problem today. Next day, tomorrow, I think we will take 2 classes on properties of integration, and I think integration everything I have done. Okay, everything is almost done. You just need to solve problems, and I will see tomorrow. I will do solve problems on integration, and maybe on the next day I will solve integration and differential calculus problems together, and then differential calculus, integral calculus, univariate will be ending for this week. And did you see the problems, guys? Did you see the problems? Oh, I also need to do a bit of improper integrals and certain application reflection principle and shifting principle. All these things are very important problem solving strategy. And there's a Leibniz rule and periodic functions, all this stuff. We need to do more problem solving. That's it. Okay, we need nothing more. We need to do some known integrals like beta integral and gamma integrals. And yeah, so that's it. Anything more? Yeah, I think these are the easy things we can do. What else? Change of variables. Yeah, that's it, I guess. That's it. So let's do this problem now, and we'll end the class. And in the next 2 classes, we'll be doing more problem solving, integral calculus and differential calculus. Okay. So okay, have you seen the assignment solutions, guys? Show that sine x by x is decreasing on 0 to pi by 2. I will tell you the steps right now. You solve it after the class and send me the solution. I will check it. Okay. First, show that you know how to show a function is decreasing, right? Since the function is decreasing, you can say that in this interval, let's call this fx. Fx is greater than or equal to f of pi by 2 in 0 to pi by 2, right? F of pi by 2 is what? It's 2 by pi. So we get that fx is greater than or equal to f of 2 by pi in this. Okay, great. The next step is that, so if we have this, observe that this comes up naturally, that e to the power x is an increasing function, right? E to the power x is increasing, which implies e to the power minus x is decreasing, right? E to the power x is increasing, e to the power minus x is decreasing, right? So therefore, we have that e to the power minus r sine x in between 0 and 2 pi by 2 is what? That means what? Sine x by x, it means what? Sine x, sorry. Split pi by 2 by 2 by pi. So sine x by x is therefore greater than or equal to 2 by pi, which means that the sine x is greater than or equal to 2x by pi. Since it's decreasing and sine x greater than 2x by pi, it means that it's e to the power minus r sine x is what? It's less than or equal to it's greater than this, a is greater than b, so f of a is less than f of b. So it's minus r 2x by pi. This is e to the power minus 2rx by pi. Since e to the power minus x is decreasing, you can also show f dash x is less than 0. E to the power minus f dash x is minus this, which is less than 0 because e to the power minus 6 is always positive. So minus of that is negative. So it's decreasing. So we get this. Right? Now, this is integrable. So let's integrate that. So therefore we get, if we integrate this, applying the property here, this property, if f is less than or equal to gx, applying this property, we get that integration of e to the power minus r sine x 0 to pi by 2 is less than or equal to integration 0 to pi by 2 e to the power minus 2rx pi by 2 e to the power minus lambda x. So you can find out this and send me the solution. Show that this is equal to this. Okay. We got the solution, right?